I want to start today with an example, with a application. So imagine that you are running a bakery. And in your bakery, you make only two items, just to make our example easy. So you make a batch of cookies, and you make a cake. And just to keep everything very simple, we're going to assume you always sell a 12-ounce batch of cookies or a 12-ounce cake. These are the things you make: 12-ounce batch of cookies or a 12-ounce cake. And your recipe for a cake consists of 3 ounces of flour, 3 ounces of butter, 3 ounces of sugar, and 3 ounces of egg. Notice if you add all that together, you get a 12-ounce cake. Your recipe for a cookie is a 6 ounces of flour, 4 ounces of butter, 2 ounces of sugar, and 0 ounces of egg. So we've got the same ingredients in both the cookies and the cake. Now the cookies don't have any egg, but we're going to represent the amount of egg as 0 ounces of egg, just so that we can have the exact same set of ingredients for both of them. I could represent this as my cookies are 6 ounces, 4 ounces, 2 ounces, 0 ounces. And my cake is 3 ounces, 3 ounces, 3 ounces, 3 ounces. We call these vectors. And we can write vectors either as a single column or a single row. For what we're doing right now, we're going to be working with them in columns. And if I have this as my vectors, my recipes, I can think about, well, what do I need to make not 1 batch of cookies, but 3 batches of cookies? So I would take 3 times my vector, 6, 4, 2, 0. And what I'm doing when I do this is I just multiply that 3 times every entry. So I would need 18 ounces of flour, 12 ounces of butter, 6 ounces of sugar, and 0 ounces of egg. And that would get me 3 batches of cookies. Or similarly, I could say, well, what do I need to make 6 cakes? So I would take 6 times my recipe for a single cake, multiply 6 times each entry to get 18 ounces of flour, 18 ounces of butter, 18 ounces of sugar, and 18 ounces of eggs. So this makes perfect sense so far. But what if instead of that, I wanted to talk about making a batch of cookies and a batch of cake, a single cake? To do this, I just need to add the vectors, and what I get is I add each entry independently. So 6 plus 3, so 9 ounces of flour. 4 plus 3 is 7 ounces of butter. 2 plus 3 is 5 ounces of sugar. And 0 plus 3 is 3 ounces of egg. And that would be to get 1 batch of cookies and 1 cake. In reality, I probably want to do some combination of all of these things during a day. So I probably want to sell maybe 10 batches of cookies, and 6 cakes. So if I put that together, I would get 10 times 6 is 60, plus 6 times 3 is 18. 10 times 4 is 40, plus 6 times 3 is 18. 10 times 2 is 20, plus 6 times 3 is 18. 10 times 0 is 0, plus 6 times 3 is 18. And doing the math, I get that I need 78 ounces of flour, 58 ounces of butter, 38 ounces of sugar, and 18 ounces of egg. If the order is 10 batches of cookies and 6 cakes, those are the ingredients I need to buy. So this idea allows us to represent more complicated things. So like I can say, well, what if I have A, and I'll just leave that as a variable for now. I want A batches of cookies and B cakes. Well, I can put these together as 6A plus 3B ounces of flour, 4A plus 3B ounces of butter, 2A plus 3B ounces of sugar, and 0A plus 3B, or just 3B, ounces of egg. We call this a linear combination. So when you can think of it as, there's two different ways to think of it. The most obvious way is to think of A and B as our coefficients, and the 6420 and the 3333 as numbers. We're doing just like our linear equation was things like ax plus by equals c. You've got a times a vector plus b times another vector is equal to some other vector. But there's another way to think about this, and that is exactly the opposite direction, because I can think of my variables as being the a and the b, and my coefficients as being these vectors. And this is maybe a more precise way of thinking about it, because the vectors are already defined. We already have those, and we combine them with our variables a and b. Each one is raised to the first power, so they're a linear combination because we're not dealing with squares or anything like that. So this is a linear combination of vectors. And a little bit of notation. So for us, the notation that we have to deal with is when we talk about a vector, we represent vectors usually with lowercase letters. And so like if I wanted to represent the cookie vector as some lowercase letter x, I could write that, but then it's not obvious that x is a vector unless I see how it's defined. So there's a couple of ways we go about that. One of the most common ways you will see is draw a little arrow on top. And if you draw a little arrow above the lowercase letter, that means that it is a vector. You will also see a lot of times, instead of writing an X like this, people will make it bold, like that. A bold lowercase letter usually refers to a vector. If you look in a lot of textbooks, this is how a lot of textbooks will represent a vector. I frequently use this. I'll write X with a little line over the top and then just a hint of an arrow on top of the line, and usually just one-sided. And the reason I do that is just because it's faster. I just do it quickly and I don't think about it a lot, but I just write that little line with a little bit of a hint of that arrow and call that good enough. So you'll see all of those. Usually when I'm writing, I will use that last one or some form of an arrow above it, but most textbooks will use a bold letter. So why don't I use a bold letter? Well, it's hard to write in bold on a blackboard or on a tablet or anything along those lines. So we have this idea of these vectors, and we can build a vector equation. So this is an example of a vector equation. And if I know how many, many ingredients I have, I can turn that vector equation, that linear combination form into an equation, into a problem to solve. So I can say, well, if I've got A times 6420 plus B times 3333, and I know that I have, let's say 15 ounces of flour and 11 ounces of butter and 7 ounces of sugar and 3 ounces of egg, then how many batches of cookies and how many cakes can I make? Well, I can just try to solve this for my for A and B. To do that, I would take and just take it on the left side and figure out what that looks like. So what is A times this plus B times that? Well, that's going to be 6A plus 3B, 4A plus 3B, 2A plus 3B, and 0A plus 3B. And on the right, it is equal to 15, 11, 7, 3. So this maybe doesn't seem like it's helped a whole lot, but now I can, by just getting rid of the vector symbols and putting an equal sign in for each equation, I have turned this into a system of equations. And we know we have rules, we have a process for solving a system of equations. We can build an augmented matrix. Like this, and then try to get it into a reduced row echelon form to solve for A and B. So to do that, I'm going to let's scale the first row by 1/6. And when I do that, when I scale the first row by 1/6, I'm replacing row 1 by 1/6 of row 1 is 1, 1/2, and 15/6. But 15/6 is, well, divide top and bottom by 3, and I get 5/2. In the second row, I'm leaving that alone. And then I'm going to add to row 2, I'm going to add row 2 plus a -4 times row 1. And to row 3, I'm going to add row 3 plus a -2 times row 1. And what that gives me is that first row stays the same, 1, 1/2, 5/2. The second row, I get 4 plus 1 times -4 is 4 plus -4 is 0. And then I get 3 plus negative 4 times 1/2 is 3 plus a negative 2 is 1. And 11 plus negative 4 times 5/2 is 11 plus a negative 10 is 1. And for my third row, I get 1 plus a negative 2 times 1 is 0. I get 3 plus a negative 2 times 1/2. And when I do 3 plus negative 2 times 1/2, I'm getting a 3 minus 1 is giving me a 2. And 7 plus a negative 2 times 5/2 is 7 plus negative 5 is 2. And then the last row stays the same, 0, 3, 3. And now I can take the second row, and I'm going to, it's already got 1 as its leading entry, so I'm going to leave that alone, and I'm going to add to row 3. I'm going to replace row 3 with row 3 plus a negative 2 times row 2. And row 4, I'm going to replace that with row 4 plus a negative 3 times row 2. And when I do that, I'm getting, the first row stays the same, 1, 1/2, 5/2. The second row stays the same, 0, 1, 1. The third row becomes 2 plus a negative 2 times 1 is a 0. And 2 plus a negative 2 times 1 is a 0. And the fourth row, the same thing, 0, 0, 0. And now I want to take all of the elements above this second row 1 and get rid of them. So I'm going to take row 1 and replace it with negative 1 with row 1 plus a negative 1/2 times row 2. And when I do that, I get 1, 1/2 plus a negative 1/2 times 1 gives me 1/2 plus a negative 1/2 is 0. And 5/2 plus a negative 1/2 is 4/2 or 2. 0, 1, 1, 0, 0, 0, 0, 0, 0. And so I can read off of this that, remember, the rows represent A, B, and my solution. So I can read off of this that A has to be equal to 1 and B has to be equal to 2. I'm sorry, A has to be equal to 2 and B has to equal 1. And so if I make 2 batches of cookies and 1 cake, I will have used up 15 ounces of flour, 11 ounces of butter, 7 ounces of sugar, and 3 ounces of eggs. So that's how many of each of the things I can make. What this tells us is that this vector equation is another way of representing a system of linear equations. I can write this vector equation, and it is another way of saying we have a system of linear equations. So this is all well and good, but mathematicians are lazy, so let's make it even simpler. Instead of representing the cookies and the cakes separately, this is my cookies. Let's just put another column right next to that for cakes. And we've built a matrix for my cookies and my cakes. And if I take and I say, well, I want to write down a vector that represents the number of cookies and the number of cakes I'm making A is cookies, B is cakes, then this should be representing the same thing. I should be able to use this to represent the same thing. And the way that I can make this represent the same thing is I can read, when I do this, I can define this matrix multiplied by a vector as, well, look for the first row, I'm going to take the first column times the first element in my vector, and the second column times the second element. And then for the second row, I'm going to do the exact same thing, just down a row. So 4a plus 3b. For the third, exact same thing on the third row. And for the fourth, exactly the same thing on the fourth row. And so this allows me to represent a system of equations as a matrix that we might call a capital A, and a vector like that we might call an x, and say that that is equal to some value b. And this b is the vector of our answers, of our solutions. So what we get then is what we call a matrix equation. And one really significant thing is when we think about how we're doing this, we're saying each individual equation in our system of equations, I can write as a really boring vector like 6, 3, just one row, times a single column vector. And if I multiply that out, I'm going to get a vector that is just a single space, 6a plus 3b. And so we can think of this matrix equation as a row vector times a column vector for each row. So we get 4 different rows, and we're taking that each row vector times a column vector. Okay, so I want to think a little bit about what do these vectors represent. So obviously they can represent a lot of things. In the example that we just looked at, the vector represented how many batches of cookies I wanted to make and how many cakes I wanted to make. But I could also do a vector that represents points in the plane. So for instance, if I did my vector, let's say 2, 1, that would be this point here, and we usually represent that as a line from the 0. So it's a arrow going from 0. The length of the arrow is called the magnitude of the vector. And so this vector, which is representing a point, we can think of a vector as being a quantity that has direction. So from the 0, 0 point, from the origin to that point 2, 1, if I draw that arrow, I've got a quantity, so a length, and a direction, because I know exactly what direction it's facing. And so this is how we typically think of a vector. A vector is it's like a number that has both a quantity and a direction. This is in contradiction to the scalar. A scalar is just a quantity. And so this is what you're used to. So like a number 3 is a scalar. A vector like 2, 1 is you can think of it like a point on the plane, or a better yet, a distance and a direction. And so if I take a scalar, 3 times a vector, I get 6, 3, and this was the basis of how we built our first vector equation. Now, when I multiply a matrix times a vector, so let's keep our 2, 1 vector, and this time let's multiply the matrix 1, 0, 0, 1. What this does, based on how we showed you how to multiply the matrix times a vector a little bit ago, this gives me we're going across the rows and down the vector. So 1 times 2 plus 0 times 1. And then for the second row, it would be across the second row and down the vector. So 0 times 2 plus 1 times 1, which is just 2, 1. So this matrix 1, 0, 0, 1 doesn't do anything to the vector. It just gives you back the exact same vector. And so because it gives you back the exact same vector, we call that a identity matrix. We will talk a lot more about that in a little bit, in a few days, a few weeks maybe. But different matrices are going to do different things to the vectors. And so like a matrix like 0, 1, 1, 0 times 2, 1. If I multiply this out, I get across the row, down the column, I get 2 times 0 plus 1 times 1. And then for the second row, 1 times 2 plus 0 times 1, which gives me 1, 2. And so this matrix just switches the x and the y from our vector. And so there's a bunch of different things that we can do, and different vectors that do different things, or sorry, different matrices that do different things to different vectors. I'm not going to worry a huge amount at this point about going further with that. We will get into a lot more details with that later on. But right now, I want to think about solving systems of equations with this. So if I look at a vector like 1 times -1, 3 as the first, this is a matrix. 1, -1, 3, 2, 1, 0, 1, 2, 1, times the vector. Now notice, because I've got 3 columns in my matrix, I need to have 3 rows or 3 entries in this vector to be able to multiply across the row and down the column. So I'm going to have x1, x2, x3. And suppose we're saying that this is equal to the vector 8, 4, 8. If I want to solve this matrix equation, I can think of this as a matrix A times a vector x is equal to some particular vector b. And so now I would be trying to figure out what is that vector x that makes this true to solve this equation. Well, if we ignored the fact that we're dealing with with matrices and vectors, and I just wrote this as some number a times x is equal to b, I could solve that by dividing both sides by a and get x is equal to b over a. Unfortunately, we don't have any way to divide matrices. So I can't do the same thing with the matrix equation. I can't do this because division by a matrix doesn't make any sense. So that doesn't work. So instead, what I have to do is I have to build my reduced row echelon form, which is 1, -1, 3, and then throw the quantity from my vector b into the last column. This makes it an augmented matrix. And now I can just go ahead and find my reduced row echelon form. The nice thing here is, in this case, my row 1 already starts with a 1, so I don't have to do anything to that. And so I can replace row 2 with row 2 plus a -2 times row 1. And I'm going to replace row 3 with row 3 plus a -1 times row 1. And when I do that, I get the first row stays the same, 1, -1, 3, 8. The second row becomes 2 plus a -2 is 0. 1 plus a -2 times a -1 is 1 plus 2 is 3. A 0 plus a -6 is -6. And 4 plus a -16 is -12. And my third row becomes 1 plus a -1 is 0. 2 plus a -1 times a -1 is 2 plus 1 is 3. Then 1 plus a -3 is -2. And 8 plus a -8 is 0. Now I'm going to replace row 2 with 1/3 of row 2. So I'm just scaling that by 1/3. So you get 1, -1, 3, 8, 0, 1, -2, -4. And the third row stays the same, 0, 3, -2, 0. Now I've got a leading 1 in the second row, and I'm going to replace row 3 because I want to clear out the information from row 3 from directly below that leading 1. I'm going to replace row 3 with row 3 plus -3 times row 2. When I do that, my first two rows stay the same. 1, -1, 3, 8, 0, 1, -2, -4. And my third row becomes 0. 3 plus a -3 is 0. -2 plus -2 times -3, well, -2 times -3 is 6, so -2 plus 6 is 4. And 0 plus a -3 times a -4 gives me 12. Now my leading entry in the third row is a 4. I want it to be a 1, so I'm going to replace row 4 with 1/4 of row 4. So I'm scaling row 4 by 1/4 to get 1, -1, 3, 8, 0, 1, -2, -4, 0, 0, 1, 3. And what I like to do is clear out the entries above. So I'm going to replace row 1 by row 1 plus row 2. That's going to make the entry above the leading row 1 in row 2. That entry above that is going to become a 0. So that gives me 1, 0, 1, 4. The second row stays the same, 0, 1, -2, -4. And the third row stays the same, 0, 0, 1, 3. Now I need to take the third row and clear everything out from the first two rows that are above the leading one in the third row. So I'm going to take row 1 and replace it with row 1 plus a negative row 3. And row 2 is going to become row 2 plus 2 times row 3. When I do that, my first row becomes 1, 0. 1 plus a negative 1 is 0. 4 plus a negative 3 is 1. My second row becomes 0, 1. Negative 2 plus 2 becomes 0. And negative 4 plus 6 becomes 2. And my third row, 0, 0, 1, 3. So my solution set is x1 equal 3, x2 is equal to, x1 is equal to 1, x2 is equal to 2, and x3 is equal to 3. So my solution vector, because my vector x is just x1, x2, x3, my solution vector is the vector 1, 2, 3. Okay, so we have the idea of we can take a matrix and multiply it times a vector to get some other matrix, which means we should have some properties of what happens when we multiply vectors, matrices and vectors. So this is properties of the vector A. So if A is an m by n matrix, so it has m rows and n columns, and u and v are vectors, and I'm going to write vectors in Rn. What this means is it has n entries. And C is a scalar. Then the following hold. First off, the matrix A times the vector that you get by adding u and v is equal to A times the vector u plus A times the vector v. And secondly, A times the scalar C times u, so the A times the vector that is composed by taking the scalar C times u is equal to the vector you get by taking A times u and then multiplying that by the scalar C. So we can distribute the matrix into a vector addition, and we can pull the constant or the scalar outside of the multiplication. And I think that is where we are going to end it for this lesson.